and hopefully everything will go fine. I have had some problems with this this recording system previously. Those who had me last year, it doesn't work quite well. It doesn't play well with my Mac, and I'm also putting it under a lot of pressure with all the different things that I've connected up to it. I can hear the fan going like crazy on it here. So sometimes it does crash, and if it does, it'll just take me a minute or two to get it up and running again, and we'll be ready to go. Okay, so all I'm going to do tonight is do a kind of an introduction to machine learning. This is the module that I'm going to be doing with you this semester. It's going to be fairly gentle, but we will also go into a little bit of detail in it. So I'm not going to go through the syllabus and things like that. I can make all that information available to you. I prefer you to just come out tonight with a kind of an overall sense of the sort of thing that where we want to be kind of at the end of the semester in terms of the different types of things that we're going to look at. And so that really means that, first of all, we kind of have to have an idea of what machine learning is. And to do that, you hear a lot of these different terms like artificial intelligence or machine learning or deep learning, and it can be difficult to maybe separate them from each other and exactly what we mean by that. So you can kind of see on the bottom here, we've got a timeline here kind of going right back to the 1950s, and this kind of shows that artificial intelligence is the overall overarching name that we have for this area, but within that, a subset of that is machine learning, and a subset then of machine learning is deep learning. Okay, so I'll be talking to you about both of those tonight, so that you kind of have a sense as we go forward exactly what they are. So it's not that these names, artificial intelligence, machine learning and deep learning, are interchangeable. They're really subsets of each other. But for all that, the machine learning and in particular the deep learning has been the major move forwards that we've made in the last kind of decade or so. So therefore, it's really the part of artificial intelligence that really works for us. It doesn't work perfectly, and it hasn't solved every problem, and there's a lot of hype around it, and I'll readdress that in a few minutes. But just to be aware that obviously it is the main game in town when it comes to artificial intelligence. Okay. So can I just make sure that you can all still hear me and everything's going fine for you there, guys? Okay, so you can all hear. That's good. So sometimes we do get crashes, as I say, and unfortunately I've forgotten to set up a little extra computer here off to my side that I normally check to see that everything is still working. So if I do disappear for a while, I'll normally just ask you to ask for some feedback and see that people are typing in, and that's simply so that I know that the system is still working and that you can all still hear me. Okay. So firstly, what's machine learning? So machine learning is an algorithm that can learn from data. So we tell it how to learn, not what to do. So most of what you might have done previously in terms of algorithm development, if you're working with computer programming languages, is you write down explicitly what it is you want the system to do. But we don't do that in the case of machine learning. What we do is we take data and we show the system how to learn from the data, but what it learns then is very much a function of what is in the data and then what we've asked it to learn from it. Okay, so one of the things to be aware of with that is that simply just having the data won't be enough. If we tell it how to learn and we tell it to learn in the wrong way, it may well learn the wrong things, and it can often give us the impression that it has learned something when it hasn't. So many of the learning algorithms have been around for decades, going right back to the 1960s. The problem with the algorithms themselves, the algorithms for learning, was that they didn't work very well. And this has been one of the problems with AI in general, is that in many cases what has happened is that the ideas have come too soon. And because they've come too soon, it means that it appears that they don't work very well, and therefore they're kind of abandoned for a while. and then people come back to them later and retry them and suddenly find that actually they're working reasonably well now. What's the difference? And the difference is that something has changed and has now made them work quite well. Okay, so what tends to happen is that when AI is tried out maybe for the first time and it doesn't work particularly well, it seems full of promise, and then it just doesn't work out, when it's used a little bit beyond its original means. What tends to happen is that it kind of goes into a hibernation, or we call it an AI winter, which is a little bit reminiscent of the idea of a kind of a nuclear winter. Okay, so I've two different diagrams of the AI winters that have taken place over the decades, and you can see here that there was a big one in the 1960s. There was a big boom there in the 1960s. That GOFI just stands. I think it's general old-fashioned AI is all it stands for. It's not something more important than that. And this was the idea that they would use things like heuristic search. Now that heuristic, another word for that is like a rule of thumb. Now, the thing about rule of thumbs or heuristics is that they're not always correct. So it's a little bit like if and else statements that you would get in computer programming languages, but the difference being that it's a little bit more probabilistic. In other words, that we say if this is the case, do this, but that mightn't be right 100% of the time. It'll be right some percentages of the time. And this is where it was used for problems in which we couldn't be definite about things. It seemed to be full of promise, but we hit a problem where things didn't seem to be working, and then we had what we call the AI winter, where we went through a full decade or more where nobody really wanted to work on AI because it just seemed like a fool's errand. And then into the 1980s we run into this other one, which is knowledge engineering, and a lot of different kind of languages and systems were come up with. You can see Prolog and Lisp and a few of those other languages where people came up with them. And these are the ideas of like expert systems, where we would try and encode in all the expert knowledge about something. So if you were trying to, fix a car engine, for example, it would go through each of the different sort of checklists that you might do in order to try and figure out exactly what the problem is. And it worked a lot on those. And again, these seem to be fairly, full of promise, but they always hit a kind of a point where they seem to not be able to go beyond that. Okay, but they were used for all sorts of things like trying to play chess at grandmaster level and so on. You had to have a huge amount of input from humans to try and implant that knowledge, expert knowledge, into the system. But again, they kind of started to hit barriers in the 1990s, and they really. Again, we landed into one of these AI winters. Now, I myself, when I was in college, I was finishing up in around kind of the 99, 2000, so in about here, I can remember doing a module on AI, and I found it really, really boring, simply because it just didn't seem to be that useful for anything, whereas I could write computer programming, C++ or Java or whatever, and I could implement all sorts of things, whereas I wasn't really sure what I could do with the AI that they were showing me. And that was more or less the feeling of everybody back kind of during those AI winters. But what then came was that ideas that had existed for quite some time then came to the fore in this idea of machine learning. Okay, so we're going to look at what are the sort of things that changed in order to allow that. I have a second diagram there just of the difference. Hopefully, if any of you are watching the recording, it'll be you'll see a bit of a jump, but it won't be major. So going back to these, this is one of the major challenges that we face when it comes to machine learning and deep learning, and it's that we're not really we don't really keep pace with the hype. And what can happen then is people assume that it's going to be able to do something. They pump lots of money into it. They then don't get immediate results, and then we could end up with another one of these AI winters. Now, I don't think that's necessarily going to happen again in this particular case, but if we think about the situation that we had back around 99, 2000, 2001, where we had a tech bubble that occurred there, and then it burst, and there was a lot of job losses, and a lot of people lost faith in the World Wide Web and the internet. They thought it's not going to be the great thing that everybody thought it was. Well, it did still turn out to be that great thing that everybody thought it was. It just came about 5 or 6 years later than everybody was expecting. Okay, so we may well see the same sort of thing happen with machine learning and AI, and it's important for you as a practitioner of it not to run away with the ideas, instead to be very realistic about what it can achieve. Okay, and just check that you're all still with me. Yeah, that's good. Next week I'll set it up a little monitor so that I can definitely see that it's still going. It's just if it freezes, I often don't know. Okay, so what's the difference this time? What allowed us to have this machine learning revolution? What changed? So there were two major developments that have brought us all the machine learning algorithms back into fashion. And the two things were big data, which again is another one of these buzzwords. We need to be a little bit careful of that. And the other thing then was computing power changed, and it went through quite a radical change. So big data, first of all, this obviously came with the internet, and with everybody being connected, it was able to gather a huge amount of data. So back in the 1990s, it was very difficult to gather a huge data set of images, for example. But once the internet started up, everybody put their images on the internet, and we all of a sudden had access to a lot of that. So, for example, this lady, Fifi Lee, who works at Stanford University, she set about making a very large data set called ImageNet. And it's made up of over 14 million images. And the important point about these images is that they're labeled. So we actually have labels to tell us what's in the images. Just having the images alone is some use, but not really a lot. But having those labeled was vitally important. So just the sheer size of the data set there is one of the things that enabled machine learning and deep learning in particular to be able to be useful to us. Before that, people were using maybe 100 images, and it just was not going to be enough. Okay. The second thing then was computing power, and this came about somewhat by accident. Obviously, we were extending the amount of computer power we have via Moore's law, but the difference here is that gaming became a big industry. There was a lot of money to be made out of it. Nvidia in particular, and they still have a huge lead in this area, were catering to gamers, and were coming up with increasingly complex machines that were no longer being used as, for spreadsheets and web surfing and things like that. These were being used specifically for gaming. And for gaming, what you need is high value graphics. To do graphics, what you're really doing is you're doing the same operations again and again, but on a very wide scale, so in parallel. So every pixel on the screen is having the same sort of operations done to it. And the operations tend to be just the exact same as each other. They're a multiply and an accumulate. Okay, so we multiply numbers together and then we add up the result. And it turned out that that particular operation is an operation that was extremely useful to deep learning and machine learning as well. So that operation being able to be done on a massively parallel way has meant that we've profited effectively from the gaming revolution by being able to use the exact same equipment to do very high performance computing for deep learning. And that's what's made this research area suddenly jump forward. To give you an idea of the jump that has occurred here, back in 1996, the ASCI RAID computer was the top supercomputer in the world at that time, and it actually maintained its position as top supercomputer in the world for a few years after that. I think almost up until 2000. It was 1.3 teraflops. That's trillions of floating point operations per second is what it could achieve. So 1.3 trillion floating point operations per second. It cost approximately 50 million at the time. It used up 850 kilowatts of power, and it was the size of a reasonable sized bungalow in Ireland. Okay, so about 1,600 square feet or 150 square meters. Now, what it was used for was nuclear testing, physical nuclear testing. There was an agreement between the major superpowers that they would stop doing that physical nuclear testing because of damage to the environment and so on. It was also, I'm sure, expensive for them as well. So what the US were doing in this particular case is they were trying to simulate that testing via a supercomputer. So that's why they would pump so much money into these things. Now, if you take the and I was updating this slide today, which is why I've found my first mistake on it that is in your notes. This is actually an NVIDIA GTX 1080 Ti rather than the 1080, which is what I had originally on this set of notes. But I changed all the a lot of the other numbers. So this is the GPU that I have on my own computer for doing deep learning. It has 11.34 teraflops. It costs around about €700. That varies depending on where you're buying it from, and it goes down over time. Uses about 250 watts of power compared to 850,000, and it's only about, it's a fraction of a square foot. It's a fairly small device. Okay, so you can see there's been almost an 8-fold increase. So as in what's in the kind of the 20 years since that, there's an 8-fold increase, and that's simply going from the best supercomputer at the time to what currently we can afford at for a reasonable price point. Just be aware, by the way, 250 watts. That's actually a considerable amount of energy, even though it may seem like only a small amount. So when it comes to things like autonomous vehicles, you can't really have a system in it that's going to use up 250 watts. Okay. Generally, I mean, what's in the Teslas at the moment is I think down around 70 or 80 watts. The system they use. So this is for training. We would use this, but we wouldn't really be able to put it in a car, because just the parasitic power that it would take from the car would be too much. So if you consider an electric vehicle that's going to be sitting in traffic, and it's not meant to be using any energy when it's sitting there, but it would actually be using quite a considerable amount. If you have all these systems that are going to take its energy from it, and of course that wouldn't be that would only be the GPU part of it. It wouldn't be all the other parts that you would have to include in as well. So when it comes to design for something like automotive, we really need to get the power consumption down. But this certainly gives you an idea of just how much power is used by these things. And of course, when you've got huge data centers full of these things, they can be a huge use of power. Okay. Jerry, you noticed you were typing there, so don't be afraid to ask a question. I can go back to anything if you have any questions, and that's the same for everyone else. I'll often keep talking until I see the question come in. Okay, so machine learning then is often referred to as narrow AI. Okay, and by narrow we mean that it sticks within a narrow boundary of its task. It's not artificial general intelligence. It's instead just a narrow intelligence. So that whole idea that you've seen in things like films like The Terminator and so on, we're not getting anywhere close to that. And indeed, even worrying about it is probably not particularly useful. There are social concerns that we have around machine learning, such as what effect it will have on jobs. Certainly, I think there's more than 3 million people in the US alone who drive vehicles for a living, and the autonomous vehicle revolution, if it comes, when it comes, will have a significant social effect there. Those are things we should worry about. Worrying about Skynet and things like that, and so on taking over the world. I think I'm just not entirely certain how we could actually achieve that right now. So that's not really something we need to worry about for some time yet. So when we talk about machine learning, we're talking about narrow AI, where it does a very, very specific task. So the goal of machine learning is not to develop a general intelligence or a universal learning algorithm. Instead, it seeks an algorithm that learns a particular task well. And then that task should result in a system that probably carries out a task correctly on most occasions. So you see I've put those two words in bold there, probably and on most occasions. This is something you also have to get used to, which is different from other types of algorithms or systems that you might work on. These are not deterministic, so we can't always get the same output from them. We can't always expect that they will operate in the same way from time to time. And we can't always be definite that it's going to work on all occasions. So we always will be working in probabilities and statistics when it comes to these. But that said, in most cases, they have outperformed the other deterministic systems, and therefore they can't be ignored from that point of view. Now, of course, most of you have either done a statistics module last year or will be doing it this year. So you'll be learning a lot more about that as time comes on. Okay. So to do this, and I've been somewhat vague here in the terms. I'm not really using the terms that might be used in actual machine learning. We'll come to those later, but I've kind of given you more broad terms that we will use for describing how the machine learning task takes place. So the first thing is that we need a task, and we need to define or limit the task. We can't just have some very wide open thing. It has to be very limited in what we're going to do. The second thing then is that we need the experience. So the system has to learn from some level of experience, and that's generally the data. So the more data we have, the more experience it's going to get. So if we take ImageNet there, which is 14 million images, that's a lot of images that we can learn from. We need a performance measure, and we need a performance measure for two reasons. Firstly, we need to know at the end of the day, how good is the system? How well does it work? But the second thing is we need to know from step to step as we're training, is the performance getting better or is it getting worse? Because if it's getting better, well, we need to do more of whatever we're doing. And if it's getting worse, we need to change our ways and go in another direction. So the performance is used for two things there, as I say. One is as a signal for our training, and another is to tell us at the end of the day how well the thing actually works. We then have a thing called a learning algorithm, and this is the bit that we usually we do the programming of. Okay, so we do program an algorithm, but the algorithm is to get something else to learn from data rather than us telling it exactly what to do. So this is the recipe by which we will improve our performance. And then of course we have the intelligence, which is usually a kind of a network or some other model that we would have. I've said the brain there, but we don't really want to get too far down the line of thinking that deep learning and machine learning are really related to neuroscience. The links there are really rather tenuous, and both fields tend to shy away from that. The neuroscientists don't like people saying that artificial neurons act like the brain, and those of us that operate with neural networks and things like that, we're very aware that we can't really answer questions of neuroscience by what we do in terms of deep learning or machine learning. So do be aware. Try not to go too far down that route of thinking of it as a brain. So there are kind of three main types of as with any field, we can divide up our field into lots of different categories, but one categorization is to categorize things into supervised learning, unsupervised learning, and this third one, which is called reinforcement learning. There's another one which is called self-supervised learning, but that's really a subset of supervised learning, so I won't mention it here at this point. So supervised learning, when training, we supply the correct answer in the hope that after training, the algorithm will predict the right answer. Okay, so we already know the right answer, and we train it with the right answers, and we hope that then later, if we come up with some new piece of data, it will know the right answer. On supervised learning, then, we don't know the answers, unfortunately. Okay, we just have some data, and we'd like to interrogate that data and maybe try and find out something about the way it's structured. So is it all clustered into different clusters and so on? Is there some way we can divide it up? Can we learn trends from that data? And that's where unsupervised learning comes in. Reinforcement learning then is quite different. It's action-based. So you have an agent. So an agent is the thing that's going to carry out the actions. You can consider the example of autonomous vehicles here. The agent would be the car. The actions are the maneuvers that it's going to make. The environment obviously is the road or whatever that it's driving on. And when it does what it's supposed to do, it receives some sort of a reward, and it then works its way back and says, okay, well, how do I assign credit for that reward to the different actions that I took? Because oftentimes you might make many actions before you get the reward, and wonder how each of those work, or what part each played. So we'll just go through a little bit more detail on these. Supervised learning, firstly, we, as in the human intelligence, must do a lot of work here. Okay, so we need lots of training data, and we need everything to be labeled. So just like Fifi Lee went and labeled or got her team and so on to label a lot of that data, we have to do the same. Now there's an example, a very simple example, is kind of like the hello world of machine learning, which is the MNIST data set. And it's a data set of handwritten numbers from 0 to 9. There are 60,000 samples of it. There's actually 70,000. We keep 10,000 away for testing, and in fact we'd normally break our 60,000 into training and validation, but again, more on that later. But you've got 60,000 samples there of little images of these digits, and you're going to try and train something to recognize handwriting from that. Now the idea, this was used for things like zip codes and so on, so it was quite useful for anything with numbers in it. But the idea is that for each one of these that we have, each one of these guys, we have to have that isn't just an image of a 0, it also has a label associated with a 0, or otherwise we can't learn from that. Okay, so that's supervised learning. Unsupervised learning then, this is kind of, to some extent, this is the holy grail of machine learning, because we'd really like to get an algorithm that could just learn by itself. So we, the human, don't have to do any work in that case. However, unsupervised learning is much more difficult with the current algorithms that we have, and it may be the only option where the data is not labeled. So if we see here the example that we have here, we've got some labeled, or we've got some unlabeled data, and we don't know anything about them. But you can see that there's a kind of a clump of them here. That's it's of low height and low weight, and then you have a clump of them that you could kind of put into large height or and large weight. Okay, so you can do that. Now this is a lovely example where it's very easy to separate them, but we're going to see examples later on where that's not so easy, and then the algorithm has a bit more trouble. So we will be going through this algorithm, the k-means clustering algorithm, in a later lecture, and you'll see more about that then. Okay, so reinforcement learning, as I mentioned already, the idea here is that you've got an agent working in an environment. It makes actions, it gets a reward from that, and then it learns from that reward and tries to assign that credit back to each of its actions. So this a bit like AI in general, it forever seems to be on the verge of revolutionizing AI, but just not yet. Okay, maybe next year, maybe the year after. This is always seems to be the case with it. And the biggest problem is to do with this environment here. Okay, we've got an environment, but the trouble is that the environment of the real world is very, very complex, difficult to model, and for that reason, when the environment gets very large, the number of different actions you can take becomes very large, and this is where the problem starts to go. But this has been very useful in terms of like they've got it to play Go against grandmasters, and it has won in that, and that's actually a much more difficult problem, as I said, than chess. It's been able to play like 1980s Atari computer games by itself and win at loads of them. So in those environments which are relatively well constrained, it can actually do very, very well. But if we take the autonomous driving example, well, we have two issues here. Firstly, the environment that it's in is very complex. The second thing is you can't really send a car out on the road to learn for itself, okay? Because what happens is it crashes into something, and it may well learn, well, okay, maybe I shouldn't have crashed that time, but it's got to do a lot of crashing and probably a lot of injuring people before it learns that it shouldn't do that. So the only place that we would be able to do this is if we did this within a simulated environment. But the big problem for reinforcement learning is things where the rules of the road, that they're fairly strict and we can write them down in a book, but something like right of way where we can have a deadlock situation and humans just tend to kind of have a kind of look at each other, eyeball each other up and wave each other on, that's much more difficult for a computer to realize to do that, particularly when there are multiple agents in it. Okay, better just do a quick check at that you're all still with me there. That's great. Have to go back. Okay, so that's good. So obviously a term that comes up all the time is neural networks. Okay, and I have an example of a neural network here, and basically this is a very, very small neural network. It probably wouldn't be particularly useful for anything. And what we've got inputs here, x1 and x2. We've got an output y, and we've got some sort of numbering system in between. So what these are, each one of these are functions, usually called an activation function, and they what they do is they multiply and accumulate, as I said earlier, which was the so multiplication and then accumulate, or a sum. And they multiply and accumulate basically the result between our number there and the weight of each one of these arrows. Okay, so you can see here that this one here has an arrow coming from there and from there, so it has something come from x1 and from x2. So it multiplies those up, adds them together, and then puts them through some form of an activation function, which will generally be a non-linear activation function. We'll come back to that later. So what happens is that our neural networks, what they're generally tasked with doing is they have to, these inputs here, x1 and x2, they're somewhat set in stone because they're our data. But the things that aren't set in stone are these weights here, which is the weight of the arrows. And so what our neural networks do at each one of these arrows is that they try and learn what they should multiply each of these x1s and x2s and each of these data points by, what they should multiply them by in order to get the correct answer out here. Okay, so that's the idea of these, and they do it on a massive scale. So I've only shown a few here, but it's not uncommon to have tens of thousands in each one of these layers, and to have, 20 layers is perfectly normal, and there are systems that have hundreds of layers and thousands of layers. There's lots of issues that come with having loads of those layers, but nonetheless, this is normal enough. So it basically does this by learning lots and lots and lots of tiny little numbers. In each case, the numbers are involved in these multiply accumulate operations that occur, which means that we can do them on GPUs. And at the end of the day, what we have is a situation where when we put in data, we expect to get the right answer on most occasions. Okay, so that's the idea of a neural network. Just massive sets of numbers in order to do it. Okay, and then what we obviously have to think about is how we're going to learn that, and we'll talk about that in a moment. So what's the deep learning bit then? So here you can see that I've got some layers here. I've got an input layer here. This might be my input here. And I've got an output layer here. Coming out to my output, but we've got some intermediate layers, which we normally call hidden layers. Okay, and if we have a few of those, we only really need one or two of those hidden layers before this becomes what we call a deep network, because it has several layers. Up until that, everything was done with it either wasn't done with a neural network, and we're going to see lots of that in the first few weeks of our machine learning. We're just going to use much more simple models. Or when we went to our first set of neural networks, it maybe only had one or two layers in it, and that would generally be known as a kind of like a shallow network. In fact, it wasn't even called shallow until we started putting lots of deep networks in, and then we said, well, we better call those other ones shallow. Okay, so that's the idea of deep learning. It's a very simple jump on top of what we had there in terms of neural networks. It's that we put layer upon layer upon layer, and we'll talk in a minute about why we might do that, but for the moment just be aware of that. So if we take something like a very famous network like the VGG network, this has there's different versions of it. Some have 16 layers, some have 19 layers, and you can see there that what we have is we have an image coming in there. It goes through some layers at one particular size. It then downsizes again. But you can also see that the layers that it downsizes to seem to become kind of deeper boxes in each case. And what we eventually end up with is we end up with this here, which I'll just zoom in on so you can see. It's 1 by 1, which is just a 1 by 1,000. So on the way in, we had images that were 224 by 224 by 3. Okay, which are the 3 obviously is red, green, and blue of our color pixels. But out comes just 1 by 1,000, and the idea was we would put in an image of something, and out would come the category, and we had 1,000 different categories. So one of those would light up, and the others would not. That would be the idea. Okay. And hopefully the network would learn in between there what to do with the pixels in order to figure out what comes out. So neural networks are just one type of architecture for learning. If we connect layers of neural networks together with these nonlinear activations in between these networks, they're said to be deep. Why do we need the nonlinear activations in between? So what if we didn't have some nonlinearity in between? Well, it turns out that if this is linear and this is linear and this is linear, then actually we can just collapse those down into one. Now that's something that for those of you that are doing the, I think you're doing linear algebra this semester, you'll hopefully come across that you can actually, if you have lots of linear operations together, you can actually combine them into one as long as you know what they are. Unfortunately, that means that having deeper layers with just linear operations will not achieve anything for us. So we have these non-linearities in between. Once we put non-linearities in between, everything becomes much more complex to try and understand. Before we go on to describe too much more of it, though, we do need to talk about some of the other things that make it easier for us to explain things. And one of the things is dimensions. When it comes to deep learning and machine learning, machine learning generally deals with smaller numbers of dimensions, and then deep learning tends to deal with very, very large numbers of dimensions. So we could be talking about 100,000 dimensions or 1,000,000 dimensions. And this can be quite confusing for people when they first come across it, because they think of the three dimensions of the world that we live in, the X, Y, Z axis, and then they might think of a fourth dimension like time. But generally beyond that, it's difficult to maybe envision what we mean by dimensions. But dimensions are a much more universal term rather than just those specific ones that we use for the 3D world. Physicists, for example, have kind of 11 or 12 dimensions that they use for string theory, but it's very hard for us to try and envision that. So because we live in the physical world, we're very aware of mapping things to that physical type of dimensions where we have 3 dimensions. And that means that our brain is not really equipped to have a picture in our head or a graph in our head of 10 dimensions or 12 dimensions or something like that. And when we get up to 100,000 dimensions, it certainly is in no fit state to deal with that. We can't draw it either. It becomes very difficult. So normally what we do is we think of things in smaller dimensions, and then we just scale that up in terms of the mathematics. So just so as you're clear about the different ways that we can set up dimensions, I've given 2 examples here because somebody mentioned points earlier. Might be the reason I'm tired, but it's not, I want to show you. So let's say we have a 4-dimensional system here, which is we have these 2 numbers here. We have a third number then, which as you can see is in meters, okay? And then we have a time, okay? So these are GPS coordinates, and they're, so you're going to have east-west, you're going to have north-south, and you're going to have height above sea level, and then a certain time. So what we're doing here is we're saying this could be somewhere that we wanted to meet. As it happens, this is the GPS coordinates of my favorite pub in Sligo. But obviously, if I was asking somebody to meet me there, I wouldn't bother giving them all that information. I'd simply say the name of the pub and the time that I was going to meet them there. Okay, and as you can see, we're already with the ish here. We're already getting into things that are statistical. It's unlikely I'll arrive at exactly 9 o'clock. But this is a way of saying something in 2 dimensions. What here I had to use 4 dimensions for. That obviously works if we have certain other information available to us. So if the person already knows where these places are. Okay, and then it's really just a matter of which one that we're going to pick. So we can have lots of different ways of representing things. And this comes to the whole idea of representation, how we represent things. So let's say, for example, that I wanted to represent the number 13. There are many different ways I can represent it. I can write it in English text, and if any of you are of non-English speaking extraction, within your own languages, you'll obviously have a spelling for the number 13. We can, of course, do it in Roman numerals. My own watch has Roman numerals on it. That can be useful at times, but not particularly useful if we want to multiply and divide, and that's generally why it went out. We can, of course, use the decimal system there. Okay, so the decimal system for 13, that's very, very useful, and it's very useful for humans because we had 10 fingers, and therefore we automatically went to use a base 10 system. But of course, when it came to using computers, operations within computers using transistors only had an on and an off, or like a switch, or a high and a low, and that meant that they had to use binary. So this is a binary representation of the number 13. Binary is quite difficult for humans to deal with, but because we have to use them in computers, we want to We want some sort of a shorthand way of jumping between the two. So hexadecimal turns out to be quite a good system for that, where it uses every 4 binary digits it incorporates into a single digit, which can go from 0 to 15. And of course we have numbers from 0 to 9, and then we use A, B, C, D, E and F for the rest of our hexadecimal. So that can all of these different representations can be useful. They all mean the same thing, but they're represented in a different way, and they have different uses depending on the situation that they're in. Okay, so how does that resolve over to what I'm talking about here? Well, let's look at something that's in 2 dimensions, X and Y here. And as you can see, the green and the blue, there's a separation between them. So if I asked you to separate the green and the blue, you know, to put a kind of a barrier between them, I'm sure most of you can spot that you could put a barrier here that would kind of go round in this direction there, okay, and would separate them reasonably well there, okay. But the difficulty is that we don't always have, you know, this human vision of what the thing looks like. We just have a set of numbers, and it's not as easy to split them up. And so we don't know necessarily to try all of these different shapes. So there's one shape that tends to be very, very useful, which is a straight line. And we like to separate things in machine learning in terms of straight lines. If we can do that, we're on to a winner straight away. But if I ask you to separate these green and blues by a straight line, you can see you've got a very difficult problem. That's certainly not going to do it. It split both the greens and the blues down the center. If I did something like that, I might say, well, okay, you know, all of these greens over here, they're on their own, and all the blues are over the other side, but I haven't dealt with all these greens here, so that's not going to work. Now, what I can do though is I can change the representation. So rather than using Cartesian coordinates, I'm going to change to polar coordinates. How many of you are familiar with polar coordinates? Have you come across that term before in maths in the past? Okay, so you've all come out. I won't ask you to do the jump between them, but it's relatively easy. You just get the Euclidean distance with the square root, square each of them, get the square root, and that'll give you the radius, and then you get the arctan of one over the other, and that'll give you the angle. So what you can see here is that when we actually change the representation over to polar coordinates, you can see now that we can now actually drive a very simple straight line down between these. So if we have some mechanism whereby we can actually change the representation of the data in some way, then we're often on to a winner when it comes to then being able to separate them with straight lines, which is the thing that we do most often. Okay. And as you can see here, what makes it easy to separate is that while the greens have basically every angle associated with them pretty much, and the blues are pretty much every angle associated with them, they are a different distance out in each case. And so that means that we're able to separate them purely on radius. Now that's exactly the same as what we just did by separating by the circle, but it's just a different way of looking at it. Instead, what we do is we get the data and we change their representation rather than changing our way of separating things. Okay. So this comes then to the idea of learning representations. What happened in most machine learning was a lot of machine learning worked on straight lines, or maybe more complex system than that. And what we would try and do is we would try and change the representation ourselves by feature engineering. But what happened when it came to deep learning is that deep learning itself, by its different layers, would learn new representations at each layer. And those different representations could then move on to another representation and another representation until we eventually got to the point where we could then start to separate them with straight lines. Okay, so this is where deep learning comes in. The deep in deep learning refers to the number of levels. Each level makes a change to the representation until eventually we can separate items with straight lines. So let's say, for example, you want a system that can look at a picture and tell you what's in it. So the idea is we want to be able to say, is it a dog in it? Is it a cat in it? What exactly is in it? But that means going from a representation of just pixel values, brightness values, to a representation that says it is this type of object or this type of object. Okay, so it's very much a change of representation, and we need to be able to separate the data out in that way. So the task here, as I said, going back to the words I used earlier, the task is what's in the picture. The experience is we'll train it by showing it lots of pictures and labeled pictures. So each picture I show it, I'll say this is a dog, I'll say this is a cat, and so on. The performance then is, what's a good measure of how well it's doing? Okay, so how do I know that it's getting the job right? Well, I know it's getting the job right if when I show it a dog, it says a dog, and if I show it a cat, it says a cat. And if I do that over thousands of images, I can just come up with a function that says, well, what percentage of the time did you get it right? What percentage of the time did you get it wrong? And there's a few different numbers we can use there. Then we have our learning algorithm, okay, which is what we're going to come back to in the next few slides. How do we get the neural network to learn the representation that's going to get it to do that job in the end? And then, of course, we've got the network itself, the intelligence network, which is full of just numbers of our weights that we're going to change. So remember, this is narrow AI. So we can decide how many types of objects we want to classify. The ImageNet competition, for example, has 1,000 objects. So therefore, it has to go from images to these 1,000 objects, and it has to be able to separate those 1,000 objects when it gets to the end. So what's in the following image? So this is very, very easy for a human and extremely difficult for a computer. How would you instruct a computer to recognize that this was a dog? Very, very difficult. So the computer doesn't need to be able to define what a dog is. So it doesn't need to be able to say, you know, that it came from the wolf or anything like that, or that it has 4 legs or any of those sort of things. We can actually use Baldrick's definition. Now, how many are familiar with Baldrick from Blackadder? There's a comedy show that used to be on the BBC. Nobody familiar with it? Or are you still there? Oh, some of you are. Okay. Some of you are familiar with Baldrick. You can click on that link later and watch Baldrick. But what happens is that they end up having to rewrite the first ever English dictionary. And Baldrick is asked to do dog. And his response to what a dog is or his definition of what a dog is that it's not a cat. Okay? In terms of our deep learning, this is actually reasonably useful to us. Okay, if we know a dog is not a cat, that's enough for us to be able to separate dogs and cats. If we have 1,000 different classes, then all we need to be able to make sure is that we can tell dogs apart from all other 999 classes. If we can do that, the system doesn't need to really understand what a dog is or define it. It needs to be able to just tell the difference. Now, if we, obviously, dogs and cats and so on, this is kind of where we start, and it's because the internet is full of pictures of dogs and cats. But when it comes to something like driverless cars, you can think of the sort of classes that you're going to want to see in an image. You're going to want to see what's a road, what's road markings, what's a barrier on the side, what's a pedestrian, what's a cyclist, what's another vehicle. And you're going to want to be able to classify them into those sort of things because you want to know what can I drive on, what can I not drive on. And that's going to be vitally important in what we do. So, again, it doesn't need to be able to define what a car is in order to be able to spot that there is a car in front of us. So going back to our dimensions, we have a problem, and it's called the curse of dimensionality. So here's the problem. We have an image. It's a relatively small image. This is much smaller than most of what you would see on Instagram or Facebook or anything like that. Image is 224 by 224 pixels and red, green and blue. So therefore it's 224 by 224 by 3. And that comes up to 150,528 dimensions. Now you might think, well, no, wait a minute, an image is only 2-dimensional. That's not what we refer to here. When it comes to information that's actually going to go into our network, each one of those pixels can vary in value, and therefore we actually have 150,528 dimensions. So it's an enormous thing, and that's not something you could visualize. And what we need to do is we need to whittle that down to kind of like 1,000 dimensions or 1,000 categories, okay? And change its representation so the computer can separate all the dogs from all the cats when we do so. So all the data points that represent dogs have to be in a different place than cats, so we can put a straight line between them. And between all the other categories as well. Now, admittedly, I keep using the term straight line. In higher dimensions, a straight line becomes what we call a plane or a hyperplane, where it's a high dimensional straight line. But nonetheless, we have to be able to put kind of these straight planes between our data to separate them out so that our system is able to tell between them. So so these are straight lines in an even higher dimensional space, but straight lines is maybe the best way to visualize them. So think about what we're seeing here. We've got a very high dimensional space, and the points that make up a dog are scattered all over the place. So it's a little bit like when you get a Rubik's Cube and the colours are scattered all over the place, and you want to change it so that you get all the colours on, all the green on one face and all the yellow on another face and the blue on another face, okay? So we want to spin and change and fold the space so that when our pixel values that originally come in get changed and changed and changed until they all kind of start to get things grouped together, where if we get a certain combination of pixels, that tells us it's a dog, and if we get a certain combination of pixels, it tells us that it's a cat. Okay, so we're going to change around this space until we are able to actually separate it. So it's I use Rubik's Cube as an example, but really it's not a great analogy, because of course rather than having a six-sided Rubik's Cube, we've got something that's a thousand sides and much harder to visualize. Okay, and we probably will never get it perfect to be able to divide between the two. There'll always be edge cases that are difficult to tell between that even humans can't do. So this idea of representation learning, we sometimes call this hierarchical learning, and the idea is that as we pass through these networks, what occurs is we change the representation more and more as we go. So we might start off with something like down the bottom here, we start to learn to see points and dots, and as we go further up it, we start to see lines, and then we start to see line segments or full lines, and then circles and shapes, and from that you start to be able to build up into wheels, eyes, things like that we can then actually see is part of some object. So the further we get up to this, we expect to see quite primitive sort of shapes here, more sophisticated shapes here, and by the time we're getting to here, we're able to start to spot some fairly sophisticated shapes indeed. So we're able to see things like eyes and so on. So at the next layer, it might learn to put line segments together. Then the next layer it might learn simple shapes, and then the next it might learn complex shapes, and at the next it might learn to make objects out of the shapes. Okay, so that's the idea of putting these into layers like this. Okay. Now, I mentioned earlier this multiply accumulate here. So each one of these is each one of these things that I showed you here is made up of what we call an artificial perceptron or an artificial neuron. So what happens is each of our inputs goes in. We will also have a bias input, and I'll say more about that later when it comes to lecture 2. What we do is we sum them up. So we multiply x1 by this weight w1, x2 by this weight w2, and x3 by this weight w3. We then sum those up and we put them through an activation function, which is some sort of nonlinear function. Again, we look at some of those as we go along, and we have an output here. And that happens time and time again throughout the entire system. So that's what each one of these are made up of. You can see I've got lots of layers here. I've only shown maybe 2 or 3 layers in my neural network here, but at each one of these layers, what we expect to happen is we expect to see more sophisticated things as we go further through the network. So that's all fine, well, but how does it learn to see? How does it learn to change those representations? How does it learn to have those increasing hierarchy there? In effect, how does it learn to change these weights at each different point to get you the right thing at each different point? Okay, so that's what we're going to look at next. So we start off with a thing called the cost function, which is going back to our performance figure. This is the thing that's going to tell us how wrong we are. Okay, and there are a good number of these cost functions, and sometimes they will be very specific to the problem you're trying to solve. They're also sometimes called a loss function. So if you come across either of those terms, they mean the same thing. So one example of a loss function that could be used for this is called a multi-class SVM, or a support vector machine. We'll be doing a full lecture on that on support vector machines later on. And so the idea here is you've got a cost function, and what we do is we add up each one of these, and if these come to a significant number, then we've got a large loss. So basically what the different parts that we have here is L1 is the total loss, or Li, sorry. Sj is the score that's given for a particular category. Okay, so for a particular category of our, let's say, 1,000 categories or dogs and cats categories, that's a particular score we get for that. And then this is the actual correct category for that. So let's say, for example, that we have a certain number that says I give this a value of 5 for it being a dog, but it's very definitely a dog and it should be 100. Then we clearly have to subtract those from each other and say, yeah, okay, you thought it was a little bit of dog, but you're not. You also give some of the values to cats and so on as well. So we need to give you credit for the different parts. And the idea here is that we need to be more sure than some value here. Okay, so we want some margin. So we don't want just to be able to say this is a dog. We want to say it's a dog, and our next guess is a cat, but that is this margin behind our idea, our guess that it's a dog. Okay, so this, whatever guess we have for the category, we have to have a certain margin between it and all the other categories, or what we'll call a certain confidence. This function max, by the way, all it does is it says, well, which is the bigger number, 0 or this? Okay. Now, if it turns out that we end up with a negative number here, that's good, because it means that 0 is the biggest here of these two, and we're just going to add 0 to our cost, so it won't make it any more costly. But if, on the other hand, we have a number here that ends up bigger than that, what will occur in that particular situation is that we will add that into our cost because we've got our numbers wrong. Okay, so this is how we include it in the cost, and this is just a margin for that. Again, as I say, we'll come back to more of that in a later lecture and go into it in detail, so don't worry too much about the maths of it there for the moment. Just that you understand that there's some function to say how badly we've got things wrong so far. Now, the learning algorithm then works as follows, right? We would take a batch of images, let's say from ImageNet, let's say we take 100 images, and we'll pass each through the network. And we'll record the score that gives for each category, and we'll do our cost function, and we'll basically total that up. We'll calculate the total loss, or the total cost for that batch of 100 images, and we'll get the average loss for that. Okay. So now what do we do at that point? So what we'll do is, one thing that you could do, this is not what we do, but you can imagine this working, is that we can just change one of the weights in the network. Now remember, there are millions of weights in the network, or in the big network. So if we just change one of the weights, that's going to take us quite a bit of time. But if we change this one weight at a time and say, well, okay, if we change this weight, put another 100 images through, does the situation improve? If it does, it was good to change that weight. If it wasn't, we should change the weight maybe back in the other direction. Okay. So this would take an awful long time because it's very, very slow. So instead, what we do is we have a system called back propagation. And what it does is it uses calculus. So it says rate of change. So basically what we do is we're saying that if the loss is changing by some amount, then our weights should all change by some amount to make that go further in that direction. Okay. So if we call all of our weights together, we put all of our weights together and we just call it theta, then we would say that the derivative, or the calculus, is dl d theta. Okay. That sounds simple enough on its own, but obviously we've got these millions of them, so how do we do it? So bear in mind that the final loss is a function of a function of a function. So let's say I've got a loss up here, and that's affected by that function, and this function is affected by these functions, and these functions are affected by these functions. This one is affected by, so this one is affected by these two, and you can see that that goes the whole way down. So how many of you have done calculus in the past? Can I just get an idea from you? I assume you've nearly all done some form of calculus in the past. Okay. So let's say you had something like cos 2x, and you want to get the derivative of this. Well, what you've got to do is you've got to firstly get the cosine of the function overall. Okay, so you could treat that as a cos x on its own and get the derivative of that. And then what you do is you multiply it by the derivative of what's on the inside here, okay, which would be just the 2 in this case. So I can't remember with cos. I'm sorry, I wrote down cos. So I think this would be something like minus sine 2x, and then multiply that by 2. something like that. Okay, and if I have that wrong, pretend I never wrote it down. Okay, but do you remember what the name for this way of doing things? Do you remember the name for this in differentiation? Yeah, it is indeed. And one of the things, by the way, I always say to my new students, the chances are when I ask you a question, the answer is on the slide. Okay, and it is indeed. It's written there, the chain rule. So this is the chain rule. And basically what it does is that because each of these activation functions is relatively simple, we know what the derivative of that is with respect to the numbers around it. And all we do is we iteratively work our way back down through this, and we can calculate the gradient or the derivative at every point along the way. And so what that means is that it's saying that if we want our loss to go down, then we need to know the gradient of each one of these so that each one can individually go down in some way to then lead overall to this overall loss going down. That's the idea. Okay. And that's useful because this is the algorithm called back propagation, which is the way of just putting it back by the chain rule back through the system in order to do that. And it's very good news because it means we don't have to do them on paper. So, okay, so you've put a batch of images through the network and you've calculated the average loss. You've determined the gradient of the loss with respect to every rate. What do we do now? So if we move every weight some little amount, in the opposite direction of the gradient. Now I say the opposite direction of the gradient because the gradient is normally given as a positive and we want to go downhill rather than uphill. We want to make the loss smaller rather than bigger. So that's why we say in the opposite direction. And if we say we're going to move, given that we know the gradient at each weight in the network, what we're going to do is we're going to move slowly down in that direction a little bit, okay, by some amount. Now we can choose what that some amount is, okay, it's known as the learning rate. But be careful when you do. If you set it too large so that it tries to learn very quickly, the danger is that it won't ever find the bottom. It'll keep jumping out of it. But if we set it too small, it will never find the bottom. Well, it will find the bottom, but just be really, really painfully slow. Okay. Now this algorithm is called stochastic gradient descent. Now you might have heard of this, or you might have just have heard of gradient descent. So the idea of going down the gradient, that's just called gradient descent. But if we take something like ImageNet, and I'm only taking 100 images in a batch, what am I doing here? I'm saying that 100 images represents the entirety of all of ImageNet, and I'm making the decision based on those 100 images. I could have 100 completely different images in the next one. So the idea is that when we randomize our images enough, that 100 images or that batch should be somewhat representative of the whole, but it won't be perfect. And that's why we have a certain amount of randomness or stochastic nature to it. And that's why we would call this stochastic gradient descent when we do it in batches like this, as opposed to, and this proper word for it is mini batch stochastic gradient descent, because sometimes batch means doing the entirety of the data set. But the entirety of the data set is too big to make every, to put 14 million images through it and then make a change. Instead, we just put maybe 50 or 100 images through in each case. Make a decision. Yes, the next 100 images might be slightly different, but that generally speaking, we're going to go in the right direction. What you're going to see then as it goes down is you're going to see this kind of very jerky nature as it goes down in value, because of that stochastic nature to it. Okay. So, right, so you've put a batch of images, 100 through the network. From this, you've modified the weights a little bit in the right direction. Now take another batch, do the same again and again and again. How long do we need to complete this? So there is an optimal time to stop. For that, we'll come back to it in another lecture at a different time. But for now, assume we keep going until we've learnt to probably recognize each of the categories correctly most of the time. Okay, so we're going to go until we can no longer improve our chances of learning the categories anymore. How long will it take? Well, originally using a few GPUs like the type I showed you there, training ImageNet would take maybe 2 or 3 weeks. A lot of people have worked on ways of doing it much quicker, either by parallelizing it over many GPUs, a huge number of GPUs, and they've also come up with some better optimization techniques to do it. As to whether some of those techniques are improvements in general or just an improvement on the ImageNet database, that still remains to be seen. So there are quicker ways, but you can still expect that for these large problems you're going to be training for a long time, and that's why these large companies like Google and so on that have huge amounts of these computational resources at their beck and call can do much more research in this area than an individual researcher. But an individual researcher with a single GPU can still do some great work, and indeed, when I get you to do some lab work as well, you'll be doing it with some quite limited resources, but nonetheless you'll do some interesting things. Okay, now once it's trained, we can make the weights file available, so we don't need to retrain it every time. Instead, we can just make that weights file available. Somebody else can download that and use it, and they can even retrain it, a thing called transfer learning, where they only change some of the weights and not them all, and that can be much quicker as well if they want to change it to do some other type of job. Okay, so we're going to finish off by just mentioning, because all we're doing tonight is going to on a whistle stop tour of all the terms that you've probably heard and trying to kind of place them all into the context. So we've mentioned neural networks, but the other thing that you've probably heard a lot about is convolutional neural networks, or CNNs. So it's sometimes called convnets, sometimes called CNNs, or convolutional neural networks. These are the same as we have described earlier, but they assume that the inputs are images. This brings the assumption that a filter that is looking for something in an image will look for it in the same way in each part of the image. So therefore, because you expect the same things, in other words, if a car is anywhere in an image, we should be able to pick that up. And this, I use the idea of a convolution. Therefore, the weights should be the same for each part of the image. So we generally make small filters like 3x3 or 5x5, and then we slide these across the image, as you've seen in convolution previously. Now, I'm saying previously because this is a slide that I would have given to my DSP students. How many of you know what convolution is? Or have seen an example of it in the past? Okay, Stephen has. Yeah, okay, and Olivia. So I'm going to assume there's okay, we're all yeses so far. There might be a few no's in there, and I'm sure that obviously we don't have everybody in tonight. Okay, so Patrick hasn't come across it before. Don't worry too much, Patrick. When we get as far as that, I will show you examples of it, and there's nice animations on the web in order to show it to you as well. And it'll be useful as well for when you go on to do the multiple view geometry and computer vision next year. Normally you might do that in a slightly different order, but or that's how it happened time wise, but nonetheless you'll be able to transfer the knowledge in that way. Okay, so then when we decide how many of these filters we're going to have in each layer, and this cuts down on the number of weights. So rather than every connection or every activation connecting to every other activation, instead we only have these filters that connect, and they share the weights over that. So it turns out that this, because it's very useful for images, people came up with it, and it also found that it saved them a huge amount in terms of memory and in terms of computation, and it turned out to be really useful in solving problems. So it's generally the main way we go about solving kind of computer vision problems now with deep learning. Okay, now I'm going to leave it at that for tonight, guys. Next week we're going to start into some actual machine learning, and the first 6 or 7 weeks we're going to be doing some fairly standard machine learning, which is very important to know before you go on to the deep learning, because many problems can be solved with those. So we'll be starting with kind of linear regression and linear classification next week, and then 6 or 7 weeks in we'll get on to our more deep learning end of things, and we'll maybe see some classification of images and things like that, but we've got to go through the machine learning end of it first. Okay, so I'll leave it at that. If you have any questions, obviously ask them there, and you can also ask them on the forum as well. If there's any questions for them there too. No problem. Okay, so great to meet you all. I'll let you go then. I think you have another class. You've got Eva at or some of you have another class at 7:30, as far as I know. On most nights, by the way, I will certainly go over the hour, because there's a good bit more in this module that I want to do. but I'll certainly make sure to be finished by 7:30, because I know, as well as the fact that you have another class, I also have another class at 7:30, so I have to be done by then. If I feel that there's one that's going to go on very long, I might just ask you to come in a few minutes early as well, but generally we'll always be done within about an hour and 20 or so, and hopefully lower than an hour on most occasions. Okay, so we'll say goodnight to you at that.